Hello, welcome back. I'm Nadimul Faisal. Today we have got METASIS Webinar number 4. Today we have a speaker, Dr. Farrukh Khalid from Indian Institute of Technology, Guwahati in India. So he'll be talking about high temperature thermochemical cycle for metal recovery and hydrogen production. Dr. Farrukh Khalid earned his PhD and Master's in Mechanical Engineering from Ontario Tech University. Currently, he is Assistant Professor at IIT Guwahati at the School of Energy Science and Engineering. Previously, he worked at Istiniye University in Turkey. His current research focuses on sustainable and renewable energy systems, particularly thermochemical cycles for hydrogen production. And he also works as a consultant for the International Atomic Energy Agency. So without further delay, may I invite Dr. Farrukh Khalid to share his screen and get started with his presentation. Thank you. Dr. Khalid, you are on mute.
Okay, fine.
I can hear you now. Thank you.
Yes. Thank you, Professor Nadim, for the introduction. And I welcome the audience for the webinar, that is high temperature thermochemical cycle for metal recovery and hydrogen production. So in this webinar or in this talk, I try to sail through the journey that how this high temperature thermochemical cycle can be used for hydrogen production. So we know that in literature there are hundreds of them being studied, some of the reactions studied theoretically, some of them has been studied experimentally, so there are a lot in the literature. However, we find very rare studies where there is a combination of this thermochemical cycle is being used for metal recovery and hydrogen production. So I will try to circumvent on that, try to, I would say, build a little bit on that, and then this is what we are going to have. So as we all know that why we all need all these kind of things. So reason is being very much obvious that we all facing scarcity of energy due to fossil fuel emissions committed by fossil fuel. And when we are extracting this fossil fuel, what is happening? We are emitting lots of emissions. So scientists and the researchers, they are looking for clean energy solutions that are not only in the operation being cleaner, but also at the source side they are cleaner. So we are looking for such kind of technologies in that. And we all know that hydrogen can be one of the potential solution for that if it is produced using renewable energy sources or the sources which are cleaner and cleaner in nature. And how to come up with this conclusion, whether what energy solution we are looking after is a cleaner option. Primarily what we do is we look at the technology from the lab scale, and then we look at its technical feasibility, and then its commercial aspects, and then later on we also look at the environmental aspect of it. And that usually terms in terms of when you talk about the industrial level and other places, usually that any energy sources we talk in terms of LCOE and mostly GWP, the potential global warming potential of that technology. So why we all need this? Because very much obvious that Earth has been regularly being heated due to this global warming issues, so which is very much pertinent. So in order to have this 1.5 degree global warming limit, it has been recommended that the reduction in energy or emissions should be by 45%. And as discussed earlier also, I told you earlier that hydrogen could be one of the potential solution for that. So in regard to that, what I am also trying to bring that any method, whatever we are using, requires energy to have it. So for example, this figure shows the primary and secondary aluminum production methods. So usually we all know that aluminum, whatever the aluminum we used, it is produced from bauxite, and then this bauxite is converted into alumina, and then from that alumina, using a Hall-Horrod process, we used it's a electrochemical process that is being used to produce aluminium. And then in the secondary, what we do is that sometime whatever the end products we have, like for example, lots of aluminum cans, and then whatever we are getting from windows and many other places, aluminum that is after their end use, we take it to the recycle factory, and then we recycle it. So that is also is an energy consuming process, because most of the time this recycling is being done usually at high temperature. So in order to achieve that high temperature, we need a source that can provide that high temperature, and that high temperature source usually comes from fossil fuel again. So there are quite significant emissions being emitted at that period of time as well. So we can say the waste product that is coming out of us, carbon dioxide and black dross when we do this recycling. So this is what typically we can have. So this figure shows that why we need to have an cut in the aluminum production related gas emissions, because it related to around 13% of the world industrial greenhouse gas emissions, and 8% of the global industrial electricity that is being consumed in the production of aluminum. And when we look at it, most of the aluminum production, the emissions are coming in from the electrolysis process. So that is around 70% is being there. So that's why people they introduce the concept of, rather than going for the fresh hunt for aluminum, they say that we can recycle it, and then that is basically a secondary, I would say, production method. So which requires around 95% less energy than we need to hunt or produce new aluminum, and it only emits 5% of the greenhouse gas emissions. So which clearly shows the benefit of the recycling, aluminum recycling. So which also help in the circular economy concept that we have. So through that we are trying to find what is the different aspect we can use it for. Now this is shows the worldwide variation in the amount of that aluminum scrap that has been there in worldwide from 1950 to 2022, and we can see that new scrap is not that as much compared to what we have the old scrap has been there. So there is a significant jump you can see in 2021 to 2022. So that is 15.5 million tons to, we can see it is jumped to 19.06 tons. So which is a quite a good significant number. So we need to have a strategy how to utilize this scrap, and we can convert it into more value-added products. One of the products that we convert is aluminum for sure, but do we convert it into some other more useful products? So that is the journey we will talk about in this presentation, that how to convert this as aluminum scrap into fresh aluminum, and or new aluminum, I would say, or the pure aluminum, we can say that, and hydrogen. So that is basically an amalgam of two processes, that is aluminum production process or recycling process, we can say, and thermochemical cycle for hydrogen production. So basically it's an integration of these two, what we learn, going to learn in coming half an hour. So that is one thing. So one of the prominent reaction what we found in the literature is aluminum reaction with the water. So it is been used to produce hydrogen. So what happened, aluminum waste, whatever you have, we take it and react it with water, and it will give aluminum hydroxide, and hydrogen is produced, and a lot of heat is being generated. So due to the exothermic nature of this reaction, it has become very much difficult to control the hydrogen production rate. So that's why this reaction is a little, I would say, a tricky one to control. So people are looking for different other methods so that from aluminium you can produce hydrogen, and then we have come up with another method that we'll discuss about it. And one of the issue with the aluminium is that it's a highly reactive element. So what happens if you left it in the environment? It reacts with the oxygen and it produces the oxide layer, that is Al2O3 layer is formed. So which basically hinder the surfaces of the aluminium, and then this reaction of aluminium with water gets slowed down, and then you don't have the enough reaction kinetics is being there. So that is another important thing has been aspect. So just to brief about what are these thermochemical cycles for the new audience, because some of the people may heard about it, may not. So just a brief concept for them. So the idea of this thermochemical cycle is basically we can say that we want to split the water thermochemically. So as we all know that any compound you can split, but you require a desired temperature and pressure to do it. So like say for example, if we have the water at environment conditions, let's say for example at environment pressure, that is ambient condition, at 1 bar, and you want to split it thermolysis process, what we call it, with the application of the heat, then you need a temperature around in the range of 2000 to 2500 degrees Celsius, which are the quite high significant temperature. But you can split it into that water molecule will no longer be thermally stable. It can split into hydrogen and oxygen. So that is we call as a thermolysis process, we can say. Otherwise, what primarily we do, and we do in the electrolysis, with the name, heard the name of electrolyzer, everywhere we heard about it. So what we are doing is that we are not splitting the water thermally, we are doing it electrochemically. So what we are doing is that we, in place of applying the thermal energy, we are applying the electrical energy, and this can be achieved if you go, let's say thermodynamically, or I would say ideally, you require 1.23 volt in order to split 1 mole of hydrogen. That is being required to do that. 1 mole of water to split, you require 1.3 volt. That's the ideal volt, but we all know that there are certain losses is being associated with it. Those will be losses due to the membrane, and then anodic and cathodic losses and all. So which is making a voltage to around 1.8 volt. And we all know that when we compare the grade wise the energy, that is thermal energy and the electrical energy, we all know that electrical energy is a high grade energy. So we don't want to utilize that energy for hydrogen splitting or water splitting. I would say rather water splitting, not hydrogen splitting. So we don't want to utilize that. So we will come up with another idea that let's split it in form of the chemicals. So they have this water splitting where they have this bunch of chemical reactions is being there, and when we look at it, the end product is basically hydrogen and oxygen, and then rest of the chemical what is being utilized in thermochemical cycle, those being recycled again, go back to their original position, and then they keep circulating in a circular form. We would say keep recycling. So it's a something like that, we can say the product of one reaction will be the inlet of other reaction. So that is one thing. So the only consumable what we can see is in a pure thermochemical cycle, as the name suggests, it's only heat and water. These are the consumables, and the products what we got is obviously I'm talking about the useful products. So when you look at the useful product hydrogen, so it will be hydrogen, and in some instances if we consider oxygen also as a product, then oxygen will also be a useful product. Otherwise oxygen will also form. However, this splitting happens in most of the cycle in literature. There are a lot of bean cycle is being there. Like for example, we have Fe2O3 based cycles, then we have sulfur iodine based cycle, and many other cycles are there. So when you want to do pure thermochemical reaction, the temperature required again are in the range of roughly 1500 to 1600 Kelvin. So which is a quite significant high number. So what people suggest that rather than being going having these kind of temperatures around 1600 Kelvin, because in order to achieve 1600 Kelvin temperature, what we need to do is again we need to split that, or we need to burn fossil fuel to achieve that. So the purpose of this whole will get defeated. So that is what has been. So we are using hybrid thermochemical cycle. So in which this temperature requirement is being reduced from I would say this 1300 Kelvin to so this temperature has been reduced from around let's say 1600 Kelvin to 800 or 900 Kelvin or maybe 1000 Kelvin. So which is quite less, and it can be achieved through renewable energy sources. So that is one of the advantage we can say talk in terms of that. And we can utilize solar energy, nuclear energy, and the waste energy in this hybrid thermochemical cycles. So one of the cycle that has been quite studied in the literature is a hybrid copper chlorine cycle. So in which there are 4 chemical reactions are there. So when you look at closely at these chemical reactions, you will find that so when you look at these chemical reactions, I would say you will find that when you do the math of it, you will find at the inlet it is only H2O, and then at the outlet is hydrogen, water, and the rest of the chemicals got recycled. Like for example, this 4CuCl will interact here, and this is the main idea is that. So this is basically it is thermochemically splitting using electrolysis process as well as using your heat. So some of the reactions, whatever being required here is exothermic, and some of them are endothermic reactions. So as you closely look at this, step 3 is basically your electrochemical, I would say electrochemical reaction, because in this reaction your delta G is positive, so which eventually equal to your that amount of electricity required. So you can convert that in terms of the voltage as well by simply delta G by NF. So we can convert it into terms of that. So how much voltage is required to split that 1 mole of hydrogen? That can be easily done. And on the basis of delta H, we can comment about the reaction, whether this reaction requires heat to proceed or it will release the heat. So as we know that when the delta H is positive, then this simply shows that the reaction requires the heat, or it's an endothermic reaction, and when it is, it will release the heat. So exothermic will be there. So that we all know. So that is what it is all about. So the idea behind this cycle, as you can see here, is about the co-production of copper and hydrogen using copper waste was the idea. So in one of the reaction, what we were introducing that the copper that is being produced is being replaced with the waste copper, and then the hydrogen is being produced in such cycle. So the setup that what we have used previously is a high temperature reactor is there, so which is nothing but a vessel is there, and in that vessel we have some electrodes were there, two couple of electrodes being placed and couple of thermometers being placed, and then the reactor is made up of stainless steel which is got heated with the heating mantle, and then we put thermocouples in order to check the temperature of the inside of the vessel and outside the vessel, and then we supplied the current, and through the current we electrolyzed the copper chlorine product that is being there, and then it is being used to produce it. So this electrolysis process was there. So what we do is first we heat this vessel using induction tapes, and once we have a desired temperature is reached, that is 773 Kelvin, then we electrolyze the this liquid copper chloride, because we know that if you supply the current to the salt that is in the solid phase, then there will be no ions will be there, so the current will not pass. So you need to change the phase. Either you have to make it aqueous, then the current will pass, or you have to liquefy it. So the melting point of copper chlorine is around 530 degrees Celsius. So we choose that temperature closer to that. So because any temperature that is beyond the melting point will be a wastage. So we don't want to do that. So in order to be on just on the safer side, that desired temperature is being reached or not, so we keep that 773 Kelvin. And then once this temperature hits, then we supplied the current through the potential stat, and then we electrolyze this product into that, and then this products whatever the we have electrolyzed product, they are further being used in different step of the cycle. So that was the one thing. And then this cycle was also studied thermodynamically. So the whole idea is that whenever we are trying to do analysis of such cycles or coming up with such cycles, so first we always approach our problem, like our group is that first we study any new concept, whatever comes is that we check its thermodynamic feasibility. And in order to do that, we usually did it through the first law and second law of thermodynamics. And once we say that the result achieves are quite acceptable one, then we go for designing of the experimental setup. So similarly, in this case also, we perform the energy and exergy analysis of the cycle. And when we did it, we found the ranges were acceptable and comparable to the other cycle in the literature, and which give us a boost to go for it, and then we design our setup. Now, coming back to the motivation, what is the reason for the aluminum chlorine cycle? So this is the current project I am handling at IIT Guwahati, and one of my PhD student, Vinay Yadav, is actively working on it, and we have the grant from the ANRF India, which is about this utilization of aluminum chloride cycle for hydrogen production and pure aluminum. So the idea was like that. As we can see there is a lot of aluminum waste and many other things is being there. So what to do and how to do. So that is what we call it as a dead metal will be there because of the thing. So the innovation comes in the phase that so far no thermochemical cycle that is based on aluminum chloride is investigated in the literature. So which give us a very good boost that there is a window opportunity where we can work off for it, and then it can be used for hydrogen production as well as for aluminum is being there, pure aluminum. So this cycle again comprises of three steps. One is a hydrochlorination step, other one is electrolysis step, you can say that. But the electrolysis, what is being carried out here is in the molten phase, so it's a salt electrolysis. So we know that there are different phases of electrolysis. So what is happening here is that we have aqueous phase electrolysis, then we have a gaseous phase electrolysis, and then we have a liquid phase electrolysis. So in this case, we have a molten salt electrolysis that we can classify it as a liquid phase electrolysis. So we are liquefying the aluminum chloride powder, and then we supply the electricity to get the aluminum and the chlorine gas. And then the third reaction that is being used mostly in the literature to produce hydrochloride gas, that is HCl gas, is basically reverse Deacon reaction. And in any of the thermochemical cycle, mostly you will find the chloride-based thermochemical cycle, whether it is a copper chlorine cycle or magnesium chloride or any other cycle you will find in the literature. You will find this reaction is being there, reverse Deacon reaction is being there. And this reaction is quite studied a lot in the literature is being there. So we try to combine that reactor. So how this will come into our reaction as well. So that was the main idea is that. So as you can see here, the first step is a very key notable step that we were looking for. That is basically a hydrochlorination reaction in which we are reacting this whatever the waste aluminum we have, and it got reacted with the HCl gas. So the good thing with this is that, as I have previously discussed about this, like for example, if you want to use this aluminum scrap, and mostly in literature what people do is that they carried out this scrap aluminum reaction with water, that is, and then it will form the hydrogen and aluminum hydroxide. But as I have discussed previously also, that this aluminum is a highly reactive element. So it reacts with the atmospheric oxygen, and then the layer of Al2O3 got formed, which hinders the reaction and that does not grow properly. So that will not be the case when aluminum get reacts with the HCl, because HCl can dissolve that layer what is being formed, and we can produce the high purity of hydrogen can be formed, and we can also get the AlCl3. So the produced AlCl3 can be again electrolyzed with the help of the electricity in this high temperature molten salt reactor, and this will be further utilized to produce the aluminum. So the produced aluminum what we have is, since it is coming from the electrolysis process, so is a electrolytic aluminum, and it is a very pure form of aluminum is we can consider it compared to what we have the scrap. So now you can see here you have the scrap and then you convert it into the aluminium. So we can take this aluminium, take it out, make the bars, whatever want, and then you can have this. So it's another would say a good way of having. And then the produced chlorine gas can be utilized to produce the HCl gas. So in which you just need to react with the steam and then having a reverse reaction, and then this HCl is again can be going back. So why we are doing this? Because right now when you closely look at it, these all HCl and aluminum chloride we can see here, they are not the consumables. Basically they are the recycle elements that is being recycled in this cycle. So the idea is behind that. Otherwise if you don't use a thermochemical cycle, just one reaction you pick it up, then there will be, you need a continuous supply of HCl gas, which could use a burden on that. That is another thing. What we can suggest is that if some industry has selling HCl, or they want to have, let's say, some issue with the HCl, like disposing of the HCl, because in some of the processes maybe the HCl will be not required for them, so they have to dispose of. So they can react with aluminium and then could produce the hydrogen and then can earn some amount of money, and they can have aluminum chloride. So if any don't want to go for this whole cycle, so one reaction also can be good. So that's why it shows us a very good understanding that what would be the setup would look like for this kind of reaction, because we know that this reaction is carried out at high temperature, as well as it is being carried out in a very corrosive environment. As we all know that hydrogen chloride gas is a highly corrosive gas will be there. So what will be the best way to proceed with it? So that is what the challenges we have associated with this: the material selection, then the reactor what you are looking for, and then corrosion, then what is the HCl handling, and then the high temperature, and then how to do the product separation, because that is very much important, like AlCl3 and HCl, because as we all know that in any chemical reaction we never have 100% conversion is there. So some product will also, I would say, reactant will remain unreacted. So the separation is another challenge that would be. So that's produce a lot of deliberation for us. Our team put a lot of thought in it, and then we come up with another solutions about it. So that I will discuss a little bit on that. And then again, same challenges associated with the step 2, that is aluminum chloride, because again this aluminum chloride is a corrosive thing, and then the material challenges come that you are melting it at high temperature and you are electrolyzing it, and how you are going to handle the salt and the products, and then the high temperature, and then material loading and product removal. So these are some of the challenges, and then we try to see as much as we can have. So I will try to do this. So that's why our idea was to design an experimental setup for this, and then simulate this hydrogen production method so that we know, okay, what the size of the reactor would be. And then similarly experimental setup for ammonium production, that is electrolysis step, and then we did the thermodynamic analysis of the proposed cycle, and then further we also do the techno-economic and the life cycle assessment of this cycle, so that it come under the definition of this green hydrogen, whether it is coming under that or not. And another idea is that whether we are having this Nelson thing is been through this or not. So there is a vision from India has been shown that in the next 1 decade, the price of hydrogen production that is will be around $1. So that is the Nelson. We say that for the next 10 years, for 1 kg of hydrogen, the price should be $1 under that. So we also see that how closely we are in this if we are using this. So this is the experimental setup we have. So we have designed basically fluidized bed high temperature reactor. So as we know that in this reaction, aluminum HCl, so the phases are important. Like for example, this aluminum waste, whatever we have, so that is a scrap that was coming from there. It was having some size was there, so we convert that into granules, small particle size particle, and we see what is the effect of the this particle, and this is mostly in the solid phase. And then HCl gas is basically a gaseous phase. So it's basically, when you closely look at it, it's a solid and gaseous interaction. So how the solid particle are interacting with the gaseous particle. So in this reactor, what we have at the top, we have a hopper is there. So where we feed our aluminum particles. So these particles is being fed. And then we have HCl gas is being fed from the bottom, and then a fluidization is happening, and then this is how this reaction goes proceed. So first we simulate it using MPPIC approach, that is multi-particle approach has been there. In this approach, what we do is basically we combine the Eulerian and the Lagrangian method, and we do the multi-particle in cell method, and this is a quite efficient method that has been used in the literature. So we use a different kind of what with the bed size, geometry, and all those things is being there. So the surface is being heated, and this. So if anybody wants to know more details about this, they can go through our article, yeah, so where we have discussed more about it. So then what was the idea is to see the effect of this HCl gas, what will be the effect of velocity of the HCl gas will be there. So we have found that in the case if the speed of the HCl gas is very high, because liter per meter, so basically it's HCl gas velocity, then the residence time of the interaction between the aluminum particle and this HCl gas is very less. However, the mixing is really good. And in the case when the reaction or the velocity of HCl is less, the interaction is not that good, mixing is not that good, but the particle have more time to, or I would say HCl has more time to interact with the aluminium particles. So when we do this, we found that in this case we have a better conversion. That is hydrogen, more hydrogen is being produced. So in this, around 80% of hydrogen is being produced compared to the other method. And all this has been experimentally optimized. And our temperature that we found, the temperature was 523 Kelvin, so which is a high temperature we assume. So as I was mentioning about the material challenge, so we were looking for the material that can sustain around that much temperature, 600-700 degrees Celsius, and also can handle this HCl gas. So we found different things, and we found that the nickel-based material was a good one. So we purchased the reactor from one of the company. But however, we give our design and everything, so it was basically that. So this is a nickel based. So main was the nickel one we have in this, not the stainless steel, because if the stainless steel is there, then it will easily corrode. However, in other salt applications, we are using this. So basically, this shows the how the distribution of the hydrogen, aluminum chloride, and hydrogen chloride gas at a same flow rate of 0.1 liter per meter, and the particle size we keep around 75 micrometer in this, and then we see what will be happening. So as you can see here, that hydrogen is lighter in weight, so hydrogen gas will collect it at the top of the reactor, and this aluminum chloride does not have that much, so it is only at the bottom, and then HCl we can only find it at the I would say surface. So the reason being is that because most of the gas has already been consumed, LCl already been get converted into our I would say aluminum chloride. So whatever just some unreacted gas has been there, so that is what we observe in that case. So similarly, we also see what is happening when we go along the length of the reactor from the top to the bottom, what is happening. So we see that as for hydrogen, you will find that if the flow rate is less, then the amount of hydrogen produced is more, because it has more time to interact with the HCl gas, this aluminum particles. And as we increase the amount of hydrogen produces less. So as you can see here, as we go up to there, then we will find that hydrogen is at the top. So that is what is being pertinent and being shown from there. So at the top, this is more hydrogen. So similar patterns were observed. However, the HCl at the top is not being there because it has already been consumed. So at the bottom, since we are feeding our reactor with the HCl gas, so at the bottom, initially when we look at this, so at the bottom that HCl has the more higher concentration, but as you go up, there will be no more HCl left because it's already been get consumed. So this is the similar pattern we observe as you go above the reactor. So similarly, we were also want to see what would be the effect of the particle size on this distribution. So it has been observed that as a smaller the particle you will have, the more hydrogen you can produce. So it clearly shows the impact of that being there. So then we compare our simulated and the experimental SCL conversion. So we also carried out the experimental step of this reaction. However, I'm not showing the graphs and other things for this because that paper is still under review. So I suggest not to show those results. So I'm not showing those results. However, just giving you a brief idea that our experimental results were in good agreement with the simulation. So that is what for different flow rates. That is the case. So within the range of 5 to 6% our model is being there. So what is we predict from MPPIC model and what we did the experiment. So they are in a good agreement with an error of around 6 to 7% been there. So this is a again experimental setup that what we used for the electrolysis process. So basically, in again as I mentioned, the challenge was this molten salt, and it's highly reactive to any kind of metal you are using or metal-based alloy. Like whether if you want to use stainless steel or another, it will be highly corrosive to that. So in order to avoid that kind of thing, what we use the alumina tube. So this alumina tube is being used. So reactor and other fittings and all those are made up of stainless steel. So this is being used, and then we use graphite electrodes in order to have this, and then alumina tubes were also being there. So that is what we use for this. If you want to know more details about this reactor and vessels, so I'm happy to share it with you if anybody is interested in that. So then furthermore, that is first we study the thermodynamic analysis of this cycle that has a fluidized bed reactor, as I mentioned, it has a molten salt reactor. So for these two processes, we also did the experiment design from everything from the scratch. However, for reverse design, we didn't do any experiment because it has been very well documented in the literature. So we take they are just experimental numbers, that is, it shows a good conversion at around 99% conversion can be achieved if temperature is around 30 degrees Celsius. So that is what we, and when we do the analysis of this cycle, overall cycle, so we found another thing is been there. Yeah. And we do perform the thermodynamic analysis. So at the end, we calculate the heat flow rates and mass flow rates and many other things. And at the end, we were interested in calculating the overall energy and exergy efficiency of this cycle, so that we may compare to the other existing cycle in the literature as well. So we did it, and we know that since this cycle, the main product is hydrogen we are producing. So up to now, we didn't talk about pure aluminium in this. So we were just taking into account hydrogen as one account. And then we see what will be the effect of the temperature and many other things were being recorded. So this cycle shows a theoretical efficiency of 44% and energy efficiency, that is basically exergy efficiency, of 48% and energy efficiency of 44%. And when we take the real conversion into picture, that is around 80% at our temperatures. So we achieve an energy efficiency of 39 and exergy efficiency of 38%. So as you closely look at it, in order to produce this, when you closely look at it, compared to the water electrolysis. So typically in the water electrolysis, in order to produce 1 kg of hydrogen, we all know that if it's a pure electrolysis process, then you require around 55 units kilowatt hour units being required if you take in all together account, whether you use a PEM method or AEM or so it is roughly around 50 to 55 kilowatt is required. However, in our case, we require only 20.28, which is around 1/3 of that, you can say, is required. However, the requirement of thermal energy is a little higher on that side. But when you do the overall conversion, you find that our cycle is much better. And this can be easily coupled to a solar thermal reactor, or it can be coupled to any waste heat plant, because the amount of heat required was around 300 and 400 degrees Celsius. So which again shows a benefit of such cycles over this, which can be coupled to either to nuclear reactors, waste heat, or they can be a good option to recover the waste heat, and a combination of the waste heat and as well as we can say the renewable energy. So this energy, electricity can come from a renewable, let's say PV plant or any other plant, and this heat comes from a waste heat, because waste heat from the industry can be in that range also. And then furthermore, in order to find the levelized cost of hydrogen, that whatever it is, so we perform the techno-economic analysis, that is we did it, and then we use certain numbers, we scale it up using some relations in the literature, and then do some math, levelized cost of electricity and all. We consider certain assumptions, so we assume how much it will be cost if we are taking the electricity from the grid, and if it is from the wind and from the nuclear, so we consider, and then the capacity, we assume that it is around 1000 kilogram per day, that is our capacity, and we are assuming that the plant runs 350 days a year, and then the total life cycle of the plant is around 30 years, which is a quite good numbers when you compare this in the literature also for these thermochemical cycles. This is 25 to 30 years usually they consider in that. And then similarly, we also include the price for the scrap aluminium, how it is going to charge for us, and then other balance of plant and other thing. And when we did it, we found that roughly there is a cost to the capex cost will be there, and then fluidized bioreactor does not cost as much, but most of the cost is going into the when you look for the scenario, different scenarios, so there were different costs will be there. So in this cost, we can see that fluidized reactor was having some good amount of cost. The battery pack was having a more cost. So we consider there are different scenarios being there. So typically we consider 4 scenarios and 5. So that is for the operation and all. And then when you closely look at that is what we are really interested in mostly. That is levelized cost of hydrogen with and without oxygen sales. So if you are purchasing the electricity from the grid, then we found that the amount of cost of hydrogen is around $3.01, and then for wind base it is 2.61, and then for nuclear it is 1.35, and for PV it is 0.78. So which clearly shows that our benefit can come into that picture. And then in order to see actually what is the hydrogen production cost per dollar, so we found that our study is suggesting around 1.04 if we are taking into account the cost of the aluminium produced as well. So that is which is quite comparable to the its counterpart copper chlorine, that is 1.28. So which clearly shows that our studies have a little more advantage compared to that. So I'm finally coming to the conclusion of this. So we have developed a novel electrochemical cycle which is used for hydrogen production and pure aluminium. And this cycle we have studied extensively through experimental simulation, thermodynamic, economic, and environmental point of view. And I didn't show you the result for the hydrogen gas produced, the experimental result, but we found that the purity of hydrogen that we produced was around 99.5%. So which can be further ultra purified using purification techniques, membranes, and other, so that it can be feed into other processes like fuel cell. Otherwise, it is a good for the industry where we need to for the decarbonization and other processes. This produced hydrogen can be a good one and can be used in the steel industry or any other processes. And then again, the produced aluminium, what we achieved was around having a better efficiency of around purity was around 99%, and energy exergy efficiencies were also 39 point, and this, so this is a wrong number. I said it was around 44%. And then the cost of hydrogen produced BR is around 1.04, and which clearly, as I said, that the NELSAL target can be achieved through this cost of hydrogen production. So, however, we were able to demonstrate the aluminum chloride cycle potential for sustainable hydrogen and aluminum production. However, there are certain aspects that need further investigation. That is going to be our future work. We are going to do. First one is that how you will have an integration of these 3 steps. So for the time being, these 3 steps work, I would say, solely, independently out of each other. But that is going to be one of the biggest challenge, how to integrate them. However, that does not limit its application. So one can choose one of the reaction and then he or she can use it for that kind of thing will be there. So that is one thing. And then at the last, I would like to thank again Professor Nadeem for giving me an opportunity to speak about this. And I also like to thank my research group at IIT Guwahati, especially Vinay Yadav, whose work I have presented to you. And I also like to thank this Science and Energy Research Board, ANRF, who's a startup grant. I got it to do this experimental and other things. And I also thankful to my School of Energy Science and Engineering at IIT Guwahati Works. And just a brief about what we do at Advanced Clean Energy Systems. So primarily our studies focus on hydrogen, e-fuel, metal recovery and sustainability. So where we study all those. So I have different, right now I have a bunch of team of around 12 people we are. And we are closely looking at these solutions where we are looking for the clean energy systems. And this is our campus, IIT Guwahati, and I welcome, looking forward to see you, the participants and the people around. They are most welcome. They just drop me an email and then we can find a suitable time. They can visit us and we have a very good campus and we can be more than happy to host them at our institute. So with this, I'm trying to close my discussion. Thank you all. And if you have any questions, please come forward and ask.
Thank you very much, Dr. Khalid. That was very insightful. So maybe now we can open for Q&A. Anybody have got any questions? So feel free to put in this chat function. So we can look for that. So meanwhile, I can ask some question. So Dr. Khalid, it means you have developed a very nice facility. So what sort of testing is possible in situ?
Like for example, we can do all this XRD and ECM and all those kind of things. We can do it for the different products. And then we recently purchased the GC, so in which we can also check the purity of the hydrogen produced. Like we are trying to do that as well. So that kind of facilities we have now. So at the institute level we have, but at the lab we have recently procured this GC and other things. So mostly this lab is dedicated to the high temperature kind of thing. So if you have any application for high temperature, like we can able to achieve a temperature in the range of up to 900 to 1000 degrees Celsius. So our reactor can handle that much temperature.
Okay, thank you. And if somebody have to test certain materials, certain design, so what sort of requirement it would be in
material side,
your lab?
we are not. Yeah, so we are not looking at the material level. So we are only looking at the how this has been possible. The product side only we are looking. So that will be a nice, as you mentioned, that since we are working in a very highly corrosive environment, so that studies also need to be carried out. Yeah, so we don't have any facility for that one now. Like morphology of the surface and all those things we don't have right now. But I think at the institute level we have those facilities. But we are not, I would say, being expert in that domain. So there are other expert people in the university, those who are being there for that.
I see. Okay. In terms of the cost, you cited $1.04 per kg, and also from nuclear it could be $1.79 per kg. So means I was looking one of the number in UK by 2050. Hydrogen production through nuclear heat, if we bring down to those numbers, say 1.5 pound per kg, that will be quite an achievement. So what challenge you see in terms of scalability and system integration for either existing nuclear plant or any future nuclear reactor?
So I don't see any challenge from the nuclear side. The challenges comes in this thermochemical cycle itself, how you are going to integrate these three steps all together. Because there are different phases being involved here. Like for example, we have solid phase, liquid phase, gaseous phase, and their interaction. And when you are scaling it up, so reactors behave differently. Like it cannot what it behave at the lab scale, it behave at a very different scale. And as I mentioned, the material challenge is going to be there. So for the time being, we assumed the assumption that this product will run for 30 years, but we don't know whether it is going to run for that 30 years or not, because until unless we develop some sustainable materials that can withstand that much highly corrosive environment, so different types of coatings may be required. So that is a different thing, I think. So that is one thing, and those are just estimated numbers, like on the assumption that, and then another thing what we are having, why this number is coming so low, is that we are also considering the production of aluminium, pure aluminium as well. So that is what it is in that. So that is what the whole idea was, that if you go closely only or solely with the thermochemical cycle, then I don't find it to be competitive until unless you combine it with the metal recovery or any such kind of industry. Like for example, maybe a steel industry, because the point is that in the steel industry, I don't know about Europe, but in India, we are looking for the decarbonization of these industries heavily. And how this decarbonization is being done, planning to be done through purging hydrogen for in this, I would say mostly in these reactors, whatever being used, smelting process and all those processes. So they don't want to burn DRI, basically reduced iron and all. So where they want to use the hydrogen for that. So if this hydrogen is produced in the same facility, let's say for example, because the mandate may come that you have to use cut off your emissions, or you have to use let's say 90% of hydrogen. So either the industry has to buy this hydrogen from XYZ, or if they have their own plant to produce it nearby them, because they already have the heat, they have the material already. So there are many things in there. So with a little investment in that, they can generate their own facility and they can pump it into like that. So the idea is about that. So that is either whether is any recovery plant or metal recovery plant, because they already work at very high temperatures. So
Indeed. Yeah. So there's a question on chat function. I guess the life cycle was 25 to 30 years. Any strategies to enhance it?
I think we closely look at the life cycle only. So what happened, not every product will behave in a similar way. So sometimes you have to replace the product as well. Like for example, some components only work for 10 years. Then you consider it that, okay, so I think 30 years is a good number. So this is what in the literature people usually use. So
Sure. Thank you. One of the question I have is on uptake of the technology. Means, do you foresee any engagement with the stakeholders who may want to develop a reactor and integrate the system like this?
So what I can see is that I don't see this whole this aluminum chloride cycle may not be the case, but people are really interested in finding the ways how to dispose of this waste aluminum. Like for example, this dross is one of the thing we have in the aluminum industry. A lot of dross is being produced. So what is the effective way of converting this dross? So if we use our hydrochlorination, let's say process is being there, then this dross can be converted into a much more valuable added product, because AlCl3 still have some market value itself, and this hydrogen as we have this. So this will be a good option in my opinion. Rather not thermochemical cycle may not be for the time being. Maybe it's maybe in upcoming 5 years or 10 years. I would say that, not an immediate one, I would say.
I see. The other question I have is on techno-economic analysis and life cycle assessment. In your modeling, did you consider the static variables or the dynamic variables?
So most of the time we assume cost and all those things are not varying with the time. So we consider this just as static. So that is the main thing.
Mm-hmm.
So in order to have this, we do the sensitivity analysis so that we try to increase the cost by 25% of the input, and then reduce also the cost by 25%. So that range is basically covering all the parameters. If there is a price variation, the thing will be there.
Sure. And in terms of getting some real data from experiment, is it something you have considered in the existing model, or there is an option in your model to add all these, any future experimental data?
So what all this techno-economic and and this LCA, whatever we consider, these are considered based on our lab scale experimental data. So these were the real, I would say this, but there has been scale it up. Like for example, we have a small 100 ml reactor. I'm just giving an example, let's say, but we consider this reactor is goes to 1000. But what we consider is this same 79% is being converted to 79% there. But we know that what you have at the lab scale cannot be replicated at the same. So when we do it at the, let's say, if you have a 1000-liter reactor, then the conversion may not be 79% exactly. But I think it's a good number to start with 79. So, but we didn't because most of the life cycle studies, what we have found in the literature on this thermochemical cycle, they consider that this conversion goes according to stoichiometry. That is 100% conversion they have considered. So we were a little bit skeptical about it, and then we try to follow the little conservation approach. So we were little conservative in that. So we only consider 80% conversion.
Mm-hmm. Sure. So in terms of temperature range, you cited earlier in your slides up to 2500 degrees centigrade. So is that the maximum temperature? As I understand, it is thermochemical cycle could be up to 650 degrees centigrade.
So the 2500 degrees Celsius is what I was talking about when you want to thermodynamically split the water. Like for example, at room temperature, if you only want to split the water through heat only, let's say for example, then I can do it if the temperature goes up to 2500, because at that temperature the delta G of the reaction become negative. Then the reaction will proceed in this direction, that it will thermodynamically get split it. Otherwise, what we do at the room temperature in the electrolysis process, we don't achieve that at 25 degrees Celsius just with the application of 1.23 volt. I'm talking in terms of ideal voltage, you can split it. So that is the whole idea is all about. So in this thermochemical cycle, it's a midway approach, we can say. Neither you want to apply 1.23 volt, neither you want to apply 2500 degrees Celsius. So you take some midway, some of the thermal energy part, some of the electrical energy part. So that's what I show in my graph. If you've seen that we required 20 kilowatt hour of electrical energy, and 53 was my thermal energy. But when you look closely, the pure thermolysis process, then it may be around 95 or something like that. That is only a pure, I would say this. But when you closely look at this exergy efficiency, exergy and all those things will be there. So that is the main idea is that.
I see. One last question from me before we wrap up the session is on corrosion of materials and structures and coating, which in my investigation, I found there's a very limited literature for thermochemical cycles. So do you think this is some problem which is too difficult to address, or any experience from your side?
So what I have is that when I was doing my PhD, so one of my, I would say, fellow mate was doing some studies on how this surfaces react at high temperature with copper chlorine. So they were testing different types of coatings for that, and then they found that this was really very corrosive environment was there. So I think it's a good investigation. So it's really, we need some material scientists who can develop such materials. So that's why when I talk about the sustainable materials we require in that. So because the point is that you can develop the coating, there will be no issues. But the point is that how long that coating can sustain and how cost effective is this? Because cost is going to eventually play an important role. Then it will become a sustainable material. So there will, I will say, a lot of window opportunities there, and there where the role of all research groups will come all together. So it will become a more interdisciplinary, I would say, or a multidisciplinary approach. Will be working for that.
Sure.
Some people design, other people design just coatings and all those things. Then it will be a very interesting problem.
Yeah, indeed. So I think we are coming toward the end of the hour. So let me thank you again for your time and your presentation, and also all the audience for your attendance today. We will share the recording of this session via link this week. And our next webinar is planned for 19th of June. That will be hopefully from Professor Siddha Sattva Basbu from IIT Delhi. Thank you very much.
Thank you, Professor Nadeem. Thanks for that.